All right, today we will be looking at linear regression, which is something we use to make predictions with, okay? So when we graph data and it seems to fit in a linear pattern, what we do is we come up with an equation that models that data, and then we use this equation to make different predictions. Some things you need to know about regression lines. Regression line is a line that describes how an effect changes in result of a cause. So it's definitely a cause and effect relationship. Regression lines are only used with cause and effect relationships, and we'll talk about that in a minute. Regression lines are only helpful with linear data, okay? So we are only going to talk about linear regression in this class. There are other kinds of regression you can do. Those will be saved for higher level math classes, but we are going to concentrate on linear regression, and so your data has to fall into a linear shape for this to be at all helpful. Linear regression is only used when there's a cause and effect relationship. So certainly we know there's associations between things like your mom's age and your dad's age typically. But those are not cause and effect relationships, and it would not make sense to do linear regression with them because you're probably not going to make a prediction with that. Okay. Linear regression is also very strongly affected by outliers, so it does throw that equation off if you've got outliers in there. And you are going to use it to make predictions, but only within the limits of the data. So for instance, if you've got data from 1980 to the year 2000, and then somebody asks you, well, can you use that data to predict what will happen in the year 2050? That would not be reasonable to do. You're only going to use the predictions within sort of the realms or the limits of your data. And of course, it works best if your model closely fits your data, meaning that it has a strong correlation coefficient. If your correlation coefficient indicates a pretty weak relationship, the linear regression is not going to be real helpful to make predictions. It's not going to give you very accurate data. We are going to do linear regression on the calculator. We could do it the long way if we wanted to, but it's ugly and gross and icky, and quite honestly, we're going to use our calculator because pretty much everywhere you're going to be, you're going to have access to technology anyways. But what the calculator does is that it draws a line, and then it measures every point, the distance from every point to that line, and it averages those out. And then it changes the line up and down, it changes the slope of the line, it remeasures those distances, and then it draws a line wherever that average distance becomes as small as possible. Okay, then we're going to look at R squared when we do regressions. We looked at correlation coefficients the other day, which was the R value. R squared is called the variance, just so you know. I should probably put this in parentheses. R squared is the variance, it's called. And it gives you an idea about what percent of whatever's happening in the Y variable, what percent of the change in the Y variable can be explained by whatever's happening in the X variable. Okay, so if I think that the farther away I am from a lightning strike, the longer the time till I hear the thunder is, the explanatory variable would be how far apart I am, and the time until I hear the thunder would be the response variable. Okay, and so I would say, the percent of change in however long it takes me to hear the thunder is this percent a result of how far away I am from the lightning. Okay, that's kind of how you would work R squared, and you'll see some examples of that. It might be a little bit confusing at first, but I will show you that. Okay. All right, so what I'm going to do here is I've given you some data, and I want you to be able to enter those into list 1 and list 2. And what you really need to be careful of is when they give you data, your explanatory variable has to go on the x-axis, or your cause has to go on the x-axis, and your response variable, or your effect, or your y, has to go on the y-axis. So and you don't have to do this, but it sure makes it a lot easier. Typically, you're going to put your whatever variable goes on your x-axis or your cause into list 1, and whatever variable goes into your y-axis or your effect into list 2. So this gives you some data about trees that were measured in the forest, and they were looking at measuring the ring size of trees according to how old they are, because I'm sure you've heard the legend that you can count the rings and trees get bigger as they get older, and the older they are, the bigger the diameter or the more rings they have. So that's kind of what this situation is about. So clearly I think you can say that their age in years, okay, is what causes the effect in their diameter or their size, okay? So actually in this case the years needs to go in list 1 and the diameter needs to go in list 2, okay? So I want you to hit pause and do that. Real quick, if you don't remember how to do that, I've already got my data in. But if you don't remember how to do that, remember you're going to go to Stat, and you're going to go into Edit, and you're going to put in the years in list 1 and the diameter in list 2. And remember to clear out a list. If you need to, you up arrow until the name of the list is highlighted. You hit clear and enter. Okay, sorry about that little interruption. Anyways, data into list 1 and list 2. Okay, so hopefully you have hit pause and done that. All right, so we've got that data in there, and now we are going to use it to do some things with it. So one of the things that I want you to do is I want you to be able to make a scatter plot of the data on your calculator, okay? And just a reminder how to do that. First of all, before we do this, I want everybody to go up to your y equals key up here, and I want you to make sure you clear out your data, okay? Clear out anything that you have in your y equals, because it'll kind of mess it up for right now. Then just a reminder that when you want to graph statistical data, you need to do stat plot. So you're going to go second y equals here. And remember, you can graph a bunch of graphs at a time, but we are only interested in seeing this one scatter plot. So I only want plot 1 turned off, or on, I'm sorry. If plots 2 and 3 are turned on, then you need to turn them off, okay? But I'm going to go into plot 1. I am going to make sure that it is turned on. I'm going to make sure that the scatter plot or the little dot plot is highlighted, which mine is. Then I need to go down where it says X list and Y list, and I need to tell my calculator where my data is. So I want my graph, or my graph to be created along my x-axis with the data from list 1 and my y-axis from the data from list 2. So you've got that, and then you're going to press zoom and 9, okay? And a scatter plot should have been created. If your calculator says dimension mismatch, what happened is if you go back to your data, remember we always have to enter data in pairs of data, and if you go back to your data you probably are missing some piece of data or have an extra piece of data or something in there, but you didn't enter your data into as pairs. So your list 1 is longer than your list 2 or shorter or whatever. So if that's an error that you got, go back and check your data. Okay? Anyways, we've got a scatter plot here, and then the next thing you need to do is describe its form, direction, and strength. And so you can see that definitely this is a linear type of relationship, which is good because we're doing linear regression. Okay, so a linear relationship, it's got positive slope, so it goes in the positive direction. So it's linear, it's positive, and it's fairly strong. It's not perfect, but it's certainly fairly strong. And then, are there any outliers? I don't think there are. Nothing that looks like way different than the rest, so I would not consider this to have any outliers. Okay, so we've got our scatter plot done, which is good. Now we need to learn to come up with our linear regression line, or our line of best fit for this scatter plot, this graph right here. Okay, so to find the linear regression, and by the way, the very first time you do this, if you didn't do it when you did correlation coefficients, you're going to need to turn your diagnostics on. So I'm going to just make sure mine are on again. So to turn your diagnostics on, you're going to go second catalog, and you don't need to do this every time, but if they aren't on, turn them on and then they should stay on. Second catalog, or second 0, and then you're going to go down to the D's, and you're going to look for diagnostics on, whoops, and then hit enter, and then hit enter one more time until it says done. Okay, and now your diagnostics are turned on. Okay, all right, so to do linear regression, you're going to do the same way you did your correlation coefficient, basically, and you're going to hit stat, and you're going to go over to calculate, and you will do number 4, which is linear regression, and you will do list 1, so second one, comma, which is above the number 7, list 2, and enter. And what your calculator will spit out is an equation, okay? And the a value, notice, gets plugged in before the x. So the a value is like your slope. So my slope in this case is 0.3577. I'm going to round everything to 4 decimal places when I write it down on my piece of paper, okay? So my slope is 0.3577, and my b, or my y-intercept in this case, is 2.5438. And the correlation coefficients you can see are there. The r squared, notice, is your variance. And so in this case, my variance, or my r squared, is 0.7889. And we will talk about that in just a second here. Okay, these are the directions. They should be on your notes too, but if you don't know how to do linear regression on your calculator, the directions are there. You can hit pause and look at it if you need to. And then we are going to get this equation copied into our y-equals so that it does graph it on the scatter plot as well. And I will show you how to do that real quick as long as we're working on our calculators before we come back to this. Okay? So if we want, we graphed the scatter plot by hitting zoom 9. Remember, this is what it looked like. And I can get the line of best fit to show on there as well. And to do that, I'm going to hit the variables button. So I'm going to go variables, and I'm going to go down to number 5, which is statistics. And then I'm going to right arrow over to equations. And number 1 is the regression equation. Okay? And it spits it out for me there. And then if you go up to your y-equals, and it didn't show up, did it? So, what happened? Let's try this again. I'm going to be in y-equals, and I'm going to try this again. Okay, variables, and number 5, and over to equations, and number 1, which is, there we go, regression equation. So sorry, you have to be in y-equals first, into y-equals, and then get your regression equation to show up. Okay, so go into y1, get it to show up, and you are there. Okay, so there it is. And now if we hit zoom 9 again, not only does the scatter plot show up, but the line of best fit shows up as well. Okay? And then you can kind of use trace along that if you want to sort of make some predictions about what's shaking down there. I'm going to up arrow so that I'm on my line, and I can hit trace and follow this equation, and I can use it really good. I can use this line to make pretty decent predictions about the diameter of the tree in different years. Okay? So here we go. We're going to answer some questions now using some algebra. All right, so all of this came from our calculator, okay? The regression line came from our calculator. I'm going to write it down here. My regression line was this. It was y equals 0.3577x plus 2.5438, okay? And I want to know what everything in this regression line means. So we're going to kind of think about this here. Okay, the y value in this case, think about what's graphed along the y-axis. In this case, the y values are the different diameters of the tree. And the x value, in this case, is the years, the age, or the years old. The slope, right here, this is the slope, okay? And the slope basically means this. So the slope is positive 3.577, and what that means is for every year that a tree ages, I'm not going to write this all out, I'm going to abbreviate it a little bit, but for every year the tree grows 0.3577 inches in diameter. Okay, so that's the slope. And then the y-intercept in this case, the y-intercept, remember, if you graph the y-intercept, it's always where it crosses the y-axis. And what I want you to think about there is that the x value is 0, okay? So always along the y-intercept, the x value is 0. In this case, the x values are the years. So what this is telling you is that in year 0, the tree had a diameter of 2.5438 inches. Okay, now Year 0 is out of the realm of our data. We don't have any, if we looked at our data pieces, we don't have any years that are close to year 0. So that's why this sort of doesn't make sense. It's a perfect explanation about why you don't use it to make predictions out of the limits of your data, okay? So that's kind of why that looks sort of weird. But that's what it would mean if we were to do it, okay? Then from that same screen that we got our linear regression from, I want to look at what the correlation coefficient is, and in this case the correlation coefficient was 0.8882. And again, I'm going to give it in 4 decimal places. And basically what that tells us is it's fairly close to +1, so that means it's a fairly strong positive, you need to give me direction, linear relationship, fairly strong positive linear relationship between the age of a tree. So I want you to put this in context for me. Tell me what variables you're referring to here. So in this case, I'm referring to the age of the tree and then its diameter. All right, and then r squared is new for you. We have not talked about r squared yet, but r squared again is the variance, it's called. And in this case, from that same calculator screen, your r squared was 0.7889. And r squared gives you a percentage. So what I can say from that is that 78.89% of the change, and you're always going to tell me what's on the y variable, of the change in this case, it would be the tree's diameter. Okay, so you can kind of follow this little format, but 78.89% of the change in a tree's diameter can be explained by, I'm going to say, or is a result of, or is caused by, any of those things work, can be explained by the tree's age. Okay, here's what I want you to notice. Right here, 78.89% of the change in this case right here is whatever's along the y-axis, the y variable. Okay, and right here is whatever is along the x-axis. Okay, and you're going to follow that same format every single time. Now, are there other things that affect the tree's diameter? Absolutely, but there is a pretty strong relationship between age and its diameter. So 78.89% of the time, if I know a tree's age, I can pretty accurately pick its diameter. Okay, is it going to work perfectly? No, but I'm going to have a pretty good prediction 78.8% of the time if I use a tree's age to predict its diameter. All right, then we are going to, again, look at the regression line equation. I'm just going to copy this. This is the same equation, same situation. I just need the data right here for myself so that I don't have to keep flipping back. All right, and so you're going to now use that equation to be able to make a prediction. Okay, so the question is, what would the diameter of the tree be if it was 7 years old? 7 is age, and remember that in this case on our scatter plot, age was graphed along the x-axis, and so you're going to put 7 in for x. And I'm going to go like this, and then solve. And when you solve that equation, you should get 5.0477 about inches. Okay, the next question, what would the diameter of the tree be if it was 60 years old? So I always want you to think about this. 60 is way out of the realm of our data. We don't have any data that's even close to being close to 60 years old. So we shouldn't use this linear regression equation to make a prediction for 60 years old. Okay? So I'm going to just write this. Don't predict out of range of data. Okay, I would get a horribly inaccurate prediction if I tried to do it for 60 years old using this equation. All right, and the last one, this time I'm giving you the diameter. It's 8.5 inches. Remember the diameter was graphed along the y-axis, so I would put 8.5 in for y. and then I would solve for x. And when I solve for that, I get x to be about 16.65 years. Okay, so that's going to give me a prediction of that. And that should do it for this lesson.